All right. Let's make sure we're all good. Yep. It's like we're all good. All right. So thank you for being flexible for those of you that are here. So if you have questions at any time, just, don't hesitate to interrupt me during the lecture. If you could type it in the chat. I have that open, but I'm more likely to hear your voice immediately than I am to see it in the chat. So, but either one, if whatever you're comfortable with. So we're moving on to nozzles and diffusers. So hopefully this is going to be the second time that you've sort of seen all this. If you haven't watched it yet, make sure you watch video 3.4. So with a nozzle and a diffuser, a nozzle, your kinetic energy, your velocity is going to speed up from the inlet to the outlet. And your pressure is actually going to drop. And that sounds a little bit counterintuitive, but if you watch the video, we kind of walk through why that is the way that it is. So these are devices that or nozzles and diffusers are one, I guess, category of devices that we're going to talk about. And all of these devices are going to be, in this class, operating at steady state. And so the typical assumptions that we're going to make for nozzles and diffusers. I should add down a little bit. Steady state. And unless otherwise specified, no heat transfer. So you'd have to consider heat transfer if you had like a really, really hot fluid or a really, really cold fluid, right? Where there was a temperature difference between the fluid that's flowing through and the ambient. But typically, we're not really concerned about that. So unless the problem specifically says something about heat transfer, we will work a problem today where it asks us to find the heat transfer for a nozzle. And so in that case, you wouldn't want to ignore it. But typically, unless otherwise specified, go ahead and say Q dot is equal to 0. There's no power generated or required within that control volume, and there's negligible changes in potential energy. Definitely changes in kinetic energy, but not potential energy. Because it's steady state, dm dt is equal to 0, and so when you apply your conservation of mass, all you're going to see is that m dot 1, m dot 2, both of those are the same, and so that's just m dot. And if you apply your conservation of mass, and we kind of look up at those typical assumptions, which by the way, you're going to need to memorize. So when we have nozzles and diffusers, we'll talk about turbines, compressors, pumps next. They all have like kind of different assumptions, typical assumptions that you'll make for this class. And so you'll need to memorize those. All right, so for our conservation of mass, purple here. So dE dt is equal to 0 because it's steady state. Dot is equal to 0 unless otherwise specified, and then changes in potential energy are equal to 0. And because that mass flow rate is the same at the inlet and outlet, you could see that just the sum of the stuff going in, which is just one thing, this m dot actually going to cancel out. And so all you're going to have left, you'll have H1, and then you'll have the kinetic energy at 1. It's the same thing at the outlet. So it's going to be up to you to be able to take that set of assumptions and figure out what the governing equation is based upon that first law, based upon that conservation of energy. So, while memorization can sometimes it can get you so far, don't cut yourself short. Make sure that you can drive it yourself and you know why it is the way that it is. All right, so let's go to the next guy. First problem, so we have steam enters the nozzle operating at steady state. We've got the temperature, velocity, and the pressure at the inlet. And I believe, yep, they tell us that mass flow rate is 1.5 kilograms per second. And, you could just kind of look at it, and based upon the fact that it's steady state, your conservation of mass is going to tell you m dot 1 and m dot 2 are equal to one another. So I didn't actually even put it in the, in my diagram that this is just m dot 1. It's m dot. And then your conservation of energy. And for all of these problems, you know, whether you write it down and show things crossed out or not, that's where you need to start. Apply your conservation of mass and conservation of energy. At minimum, that's what you're going to need to do. So conservation of energy, we just saw just a few minutes ago. If we say Q dot's equal to 0, W dot's equal to 0, potential energy changes are equal to 0 because those are the typical assumptions. So typical assumptions, you know, steady state, dot's equal to 0, W dot's equal to 0, changes in potential energy are equal to 0. And if we make those typical assumptions, what we end up with is H1 plus V1 squared divided by 2 plus, oops, not plus, equals H2 plus squared at state 2 divided by 2. Okay, so we're supposed to find velocity at the outlet. And so I think probably that conservation of mass is a good place to start. And if I look at sort of what I'm given, I've got the velocity at state 1, it's 80 meters per second. And then as long as I have two independent intensive properties at state 1 and state 2, that will be enough to fix my state. Temperature and pressure, they're independent of one another as long as it's in the single phase. So hopefully we are in the single phase. Let's just go ahead and see. So it's state 1, 280 degrees Celsius and 20 bar. So I'm going to go to my saturated tables to figure out what phase I'm in. And looking at A3, I can see that, well, at 20 bar, the temperature would have to be 212.4 degrees Celsius in order to be saturated, and we're at 280 degrees Celsius. So clearly it's superheated, so I need to go to table A4, my superheated tables. And here we go. So this is table, I just want to zoom in so we can actually see it. So this column is temperature, this is, oops, this column is specific volume, this is enthalpy, actually no, this is internal energy, apologies. Internal energy, and this is enthalpy. And then the last one is something we haven't talked about yet. So you can see here's my H1, 2976.4. And then we could go through a similar exercise with state 2. So state 2, what was it? State 2, yeah, 7 bar and 180 degrees Celsius. You can go to your saturated tables and figure out it's superheated as well. And so also in table A4, you can see it's 7 bar and 180 degrees Celsius. There's your H value, 2799.1. So I'm going to go ahead and write that on my work here. So actually, I'll just see. Yeah, so H2 T799.1, H1 2976.4, and both of those are kilojoules per kilogram. All right, so now I just need to rearrange and solve for V2. So if I do that, let's see what I'm going to end up getting. V2, H1, H2 plus E1 squared. I'm going to have to take the, oops, like that. I'm going to have to take the square root of all of this. Perfect. So you could see that, you know, my units here, this is going to be kilojoules per kilogram. This guy is going to be meters squared per second square. And if I want this guy to be in meters per second, obviously that first term under the square root is going to have to be converted to a meter squared per second square. So I'm going to kind of keep that in mind as I'm writing. This is going to be, let's see, so 2 times 2976.4 minus 2799.1. Both of these are in kilojoules per kilogram. And if I break it down to the base unit, a kilojoule is 1,000 joules. Joule is a newton meter. It's a kilogram meter per second squared. And then of course I've got my V1 over there. So V1 squared is the 80 meters per second squared. Then I just need to take the square root of all this stuff. Perfect. And so I think that should probably take care of my units there. Kilojoules, kilojoules, joule, joules, newton, newton. And I'll have a meter squared per second squared plus the meter squared per second squared. So everything kind of checks out there. So let's see. So my V2 ends up 600.8 meters per second. If you find that, you get an answer that just absolutely does not make sense, for your velocity or, some number doesn't make sense in a nozzle or diffusion problem, 9 times out of 10, it's a conversion factor problem. All right, so that is part A. And then we also want to find the inlet and the outlet flow areas. So for this guy, since I know that mass flow rate, let's see what this can get me. So if I say that mass flow rate, I define it at state 1. So A1, velocity at 1 over specific volume at 1. Of course, I will have to make the assumption of 1D flow in order to use that equation. Otherwise, I would have to define the mass flow rate with an integral velocity over specific volume integrated with respect to area. And looks like I've got V1, the velocity at 1. I do need the specific volume at 1. So this is, and I already fixed my state. Go ahead and kind of rearrange this for area at 1. So this would be m dot specific volume at 1 over the velocity. This is 1.5 kilograms per second. And then the specific volume, this is in my superheated tables again. So it was at 20 bar and 280 degrees Celsius. And in my superheated tables, about that, superheated tables, it looks like that's going to be 0.12 meters cubed per kilogram. So I'm going to go ahead and add over here 0.12 meters cubed per kilogram, and then divided by 80 meters per second. And what that actually should get me is something in meters squared. I want it in centimeters squared, so just another little unit conversion issue. I end up getting 0.00225 meters squared, and if I want to put it in centimeters, there we go. I end up getting 22.5 centimeters squared. That's the area at 1. And then if I want to get part C, if I want to get, actually wait, I think we still categorized it under part B, didn't we? If I wanted to get the area at 2, I could do the exact same thing. M dot equals A2 times the velocity at 2 divided by the specific volume at 2. But I think instead what I'm going to do is I'm going to say, well, I know M dot 1 is equal to M dot 2. I could define those as A1, 1 over the specific volume at 1, A2, 2 over the specific volume at 2, and then just solve for A2 that way. And the reason I'm going to do that is because when I plug this guy in, I'm just going to leave him as centimeters cubed. And so this is going to be the velocity at 1, velocity at 2, Of course, I'm going to have a specific volume there as well, V2 over V1. V1 I already got. That's this guy right here. It's the 0.12. I calculated V2, the velocity at 2 to be 600.8 meters per second. So I got that. This guy was given to me. I calculated that. Got this. The only thing I need to do is get the specific volume at 2. So this is at 7 bar and 180 degrees Celsius. 7 bar and 180 degrees Celsius. It looks like that's my specific volume right there. 0.2847. So I will write that over here. So 0.287 meters cubed per m. Then that means that this guy is going to be 7.11 centimeters. Not cubed, squared. Okay. So this next guy, I realized this morning that I had put things and I had started writing kilojoules per kilogram, and it won't be the last time I do such a thing. Hopefully it won't be like a lot. All right, so I'm going to erase this stuff because we're not in SI units, we are in English units. So go ahead and fix this. So what they ask us, they give us a nozzle, they give us the inlet temperature, and then they also give us, by the way, they give us, write it in blue before I go over to the find, they say it's got negligible kinetic energy at the inlet. So I'm going to kind of make a little note here. If I'll say for a nozzle. For a nozzle, if the kinetic energy at 1 is not given and not possible to find, and assume kinetic energy at 1 is approximately 0, because the kinetic energy at the outlet is so much bigger, right? And so it's a sort of a scaling analysis, right? What terms are going to be the most important terms in your equation? And when you compare the kinetic energy at the inlet, it's going to be much, much smaller than the kinetic energy at the outlet, right? And so, you know, I would encourage you to kind of prove that to yourself, even when you have that kinetic energy, or even when you have a way to find that kinetic energy, or you're given something, how to find the kinetic energy at the inlet, calculate things by just using 0 instead. It's not going to change things that much. Now, if you're given some information about the kinetic energy or the velocity at 1, go ahead and use it. But this is just, you know, don't have the information. This is an option of how to proceed. All right. So we can assume that it's an ideal gas, and we want to find the heat transfer in BTU per pound mass of air flowing. So remember our typical assumptions. Typical assumptions for a nozzle and a diffuser: steady state, U dot is equal to 0, W dot is equal to 0, changes in potential energy are equal to 0. And so, you know, unless otherwise specified, go ahead and make those assumptions, right? They told us steady state, potential energy is equal to 0, W dot is equal to 0. But in this case, they don't actually, they want us to figure out, well, what is the heat? So I don't want to just say it's 0, done. I'm going to actually calculate it. So they ask for it in BTU per pound mole, or pound mass. I keep on saying pound mole, per pound mass of air flowing. So let's just take a beat and think about what our conservation of mass tells us, which it's one inlet, one outlet, steady state. All it's going to tell us is that m dot is the same throughout. Now their conservation of energy, take a hot second because I've got this is a little bit different from our typical nozzle. So I'm going to go ahead and just write everything out just to make sure that I'm not missing anything and that I derive the correct equation. So I've got dE dt equals q dot minus w dot equals the sum of the m dot h's plus kinetic energy at the inlet plus potential energy at the outlet, and then it's the same thing minus the same thing at the outlet. All right, so I'm going to go ahead and let me cancel out some things, right? Steady state, that goes away. Potential energy changes, those go away. I don't have any of this W dot, but and they told me that I can go ahead and kind of ignore that kinetic energy at the inlet because it's not going to change things that much anyway. So let's go ahead and get rid of that guy. Oh, I mean, not get rid of that guy, get rid of that guy. There we go. All right. So it's our Q dot. Perfect. So our Q dot is going to be, and it's going to be the stuff going out minus the stuff going in. So it's going to be, an M dot here. So M dot times H2 minus H1 plus V1 squared divided by 2 divided by, or V squared 2, V2 squared divided by 2. Ugh. Okay. So now there's my equation, and that Q dot, he's going to be in BTU per second. So a little bit smaller. So BTU per second, units of energy per unit time. And your M dot might be in pound mass per second. I don't know what that mass flow rate is. I don't really have any way to calculate it, but it doesn't matter because I'm dividing through by that mass flow rate anyway, right? So if I divide Q dot by M dot, of course you could see that that's going to give us BTU per pound mass, which is exactly what we have here, BTU per pound mass. Perfect. All right, so at this point, I've got the velocity at the outlet, and I know the temperatures at state 1 and state 2. And once again, you've got air, and so we're going to go to our ideal air tables. So this is table A22E. That's where you're going to find these guys. Let's go look and see if we can get those H values. So our steam tables need to get out of there, and I need to make sure I'm going to the English unit tables. There we go. All right. So this is our A22E, and you can see our T1. Let's see. T1 was 507.20. I'm sorry, this one. That is the wrong. There we go. So this is T1. This is T2, right? Nope. This is T2. This is T1. Yes. All right, so here's our H values for each of those. No problem. So I think it's just kind of plug and chug here, just kind of a glorified exercise in unit conversions. So little q, which is equal to that Q dot expressed per or divided through by M dot. It's going to be H2 minus H1. H2 is 119.48 and H1 is 172.9, and the units there are BTU per pound mass, which is great. Those are the units that I need. But then I've got this pesky kinetic energy term that I've got to deal with. So it's going to be 1450 feet per second squared divided by 2. And so I need to make sure that both of those are going to be in BTU per pound mass for my units to work out correctly. And so sometimes English units are a little bit messy. I know I need BTU on the top. I need some sort of conversion factor involving BTU that might get me a little bit closer to where I need to go. So where I'm going to look is my conversion factor sheet. And I've highlighted the ones that are pretty useful to me here. So 1 BTU is 778.17 foot per pound force, and then a pound force is 32.174. I'm going to round it off to 32.2 pound mass foot per second squared. So let's go ahead and put that on there. So 1 BTU is 778.17 foot pound force, and my 1 pound force is going to be 32.174. If you want to keep the 174, you can. I'm going to be lazy and write 0.2, and then this is pound mass foot per second squared. And I think that should work out nicely. So let's just make sure that we end up, hopefully what we end up with is BTU per pound mass. Let's make sure that everything cancels out. So I have foot squared. Where are you? There we are. I have foot squared, second squared, pound force, and I think that will make my units work out the way that I want them to. All right, so little q, which is q dot divided by m dot, ends up being negative 10.9 BTU per pound mass. And so one thing that we might notice is that, like, if you look at the delta H, you've got this being the delta H. So 172 and change minus just about 120, you could see that change in BTU. I mean, you've got something around 52 and change BTU per pound mass for that delta H. And then really, like, this guy right here is effectively the change in kinetic energy, because the kinetic energy at 1 was 0, right? So the change in kinetic energy is this 1450 squared divided by 778.17 times 32.2. So just, you know, as far as like a scaling analysis goes, you can kind of see why we typically ignore that cube, because it's usually pretty small. Okay. Okay. So let's do the next guy. So this is another problem where we do have air. It's another English unit problem. But this one, we are going to go ahead and ignore that heat transfer. So, you know, once again, typical assumptions that we're going to memorize for this class. And I'm going to write them up here. And then if they, I'll kind of go through the problem and make sure that they're not telling me, actually don't ignore that. So steady state dot equals 0, W dot equals 0, changes in potential energy equals 0. So, all right, so we got air enters a diffuser at steady state at 540 degrees Rankine, 15 psi, and a velocity of 600 feet per second, exits at 60 feet per second. And they don't tell us what the area is, but they do tell us the ratio of those two areas, with the area at the outlet being a lot bigger, or being bigger, I should say, than the inlet. Assuming the ideal gas model for air and ignoring heat transfer. So they do tell us to ignore heat transfer, but they didn't actually tell us any of these other typical assumptions, like super secret assumptions that we're going to make. So, yep, steady state, Q dot equals 0, and super secret option number 2 is W dot equals 0 and changes in potential energy are equal to 0. They didn't tell us anything to sort of tell us, don't actually make that assumption, right? Don't actually calculate what the change in potential energy is. So T2 and P2, that's what I need. So I can, let's go ahead and start with, you know, conservation of mass, conservation of energy. So this is m dot 1, it's m dot 2, just equals m dot, and this is just a regular old diffuser. If I apply my first law, and I made all of those assumptions up there that I applied in, or that I wrote in purple, I'm going to get H1 plus V1 squared divided by 2, H2 plus squared 2 divided by 2. And so the idea is if I can get H2, I can get T2. So I'm going to get T2 at H2. Because I've got air, and if I think about those ideal air tables, all I really need is the temperature, right? It's an ideal gas, and for an ideal gas, your enthalpy is a function of one thing only, and that's temperature, right? So kind of another thing that makes ideal gases very useful. All right, so perfect. Let's go ahead and get H2. So H2, it's going to be H1 plus be 1/2. It's a little bit down. 1/2 times V1 squared minus, it's a minus, V2 squared. So I can go ahead and get H1, so 540. Let's go ahead and go to those ideal air tables. Once again, it is also English units, so let's get there. There it is. All right, so A22E, we are at 540. So you can see what our enthalpy value is, 129.06. So let's go ahead and go there. 129.06, and this is going to be in BTU per pound mass plus 1/2, and I've got my 1 squared minus V2 squared. So V1, 600 second squared. V2 is 60 second, square that guy. And then of course I need those, if this guy is in BTU per pound mass, this guy is in feet squared per second squared, I need this guy to be in BTU per pound mass. So it's the second term that I'm going to need to some unit conversions at. So 1 BTU, 778.17. I got it. 0.17 foot force, and a pound force is 32.2 pound mass foot per second squared. I'm sorry, I just realized that you can't see behind my head. I apologize. So I think that should do it, and we end up getting a final answer. 136.17. And that's BTU per pound mass. And of course, that's not the final thing that I need. I need P2, which is the temperature as a function of enthalpy. That's all we need. And that's going to be, let's go ahead and get that guy. So our enthalpy was 136.17. So that looks like right there. And so your temperature would be in between there. And I actually interpolate for something really close to 570. So it's 569.6. That's degrees Rankine. So that's part A. And then part B, what are we doing? We are finding the pressure. So we need it in PSI. And I've sort of exhausted my conservation of equations. Sort of, not exhausted them. However, I am going to sort of, see, I think I am going to come back to my conservation of mass. The reason being is because I know that m dot 1, dot 2 are equal to another. I also know that A1, specific volume at 1 is equal to A2, V2 over my specific volume at 2. And then of course, those specific volumes, I can go ahead and I can use my ideal gas law to get those in terms of pressure, which would be really useful. So this will be A1, T1. This is going to be R T1 over 1, A2 V2, R T2 over P2. So you could see that R value cancels out, but so you don't need it. But do know that this is English units, and so like if you did need to calculate that, need to get this molar mass. It's in table A1E. It is the number for air. It's still 28.97, but the units are pound mass per pound mole. And look on your unit conversion sheet, page 3 or 2 or 3 or something like that, on your packet with all those unit conversions. At the very bottom, they've got 3 values for that universal gas constant. You got 1 in SI units, and then you've got 2 in English units. 1 is 1545, and it's foot pound force per pound mole Rankine. There's another one that's in BTU, so 1.986 BTU per pound mole Rankine. That the denominator is the same, 28.97 pound mass per pound mole. So just do be aware. It just depends on what units you need. In this case, we didn't need it, but I do want to sort of draw attention to that so that you're aware of that if you need it. All right, and so at this point, all I need is, what do I need? I need P2. So this is going to be P1, A1 over A2. We've got that ratio, right? A2 over A1 was 8, so this will be 1 over 8. And then this will be velocity at 1 over the velocity at 2. What else do I have? I have temperatures. I got T2 over T1. So I end up getting 19.78, and this is in PSI. Perfect. This is as far as I plan on going today, because the next section is on turbines, compressors, and pumps, and so it's a good natural stopping point. So make sure that before we meet on Wednesday, which hopefully will be in person, but that will be video 3.5. So just make sure that you watch that. I think probably we'll be back in person, but yeah, fingers crossed. Fingers crossed. Okay. All right. Thank you very much. There are office hours tomorrow, virtual with Aiden, and then Wednesday I'll have office hours as well. Okay. Thank you very much. I appreciate it. Y'all have a good one. Okay. Thank you.